Imagine you had a situation where there was a river flowing, and in our picture we're going to make the river flow to the right. And we know that the velocity of the river is a certain amount. Imagine I have a guy sitting on the shore observing all this, and I have a boat. Now my boat, this is going to be a horrible looking boat, so get over it. If I get in my boat and I float downriver, I don't turn the engine on, I don't row it or anything, the velocity of this boat relative to the shore over here, I'm going to put S for shore, is going to be equal to the velocity of the river. This guy will see the boat flow by at the same rate that the river does. However, if you've got a motor on your boat and you fire it up and you get it going in the same direction as the river, this guy will see that boat go by much faster than he would if it wasn't moving relative to the water. And if you turn it around and go the other way, he'll see it going by slower than it would if it wasn't in this moving water. As a matter of fact, if the velocity of the boat and the velocity of the river are the same and you go opposite the current upstream, that boat would appear to be standing still from this guy's point of view. What we're getting at is that if you want to figure out how fast the boat is going relative to the shore, you're going to have to do some vector addition. And the way this would work is that the velocity of the boat relative to the river, which is what this really is, plus the velocity of the river relative to the shore, which is what this really is, the vector sum of those two things will be equal to the velocity of the boat relative to the shore. Now we can kind of make a more generic statement of that to say that the velocity of A relative to B plus the velocity of B relative to C equals the velocity of A relative to C. So now let's do an example. A boat with speed in still water of 1.85 meters per second heads directly across a river whose current is 1.20 meters per second. A, what's the velocity of the boat relative to the shore? And B, if the river is 110 meters wide, how long will it take to cross and how far downstream will the boat be? All right, we've got a couple parts here, but let's start with what we're given. Okay, we're told that the boat can travel in still water 1.85 meters per second. In other words, the velocity of the boat relative to the water, or the river I should say, is 1.85 meters per second. The direction of that vector, where it says we're moving straight across the river, so let's draw it that way. So that's the velocity of the boat relative to the river. Now it also says that the current is 1.20 meters per second. I'm going to draw, first I'm going to write that. Velocity of the river relative to the shore is 1.20 meters per second. I'm just going to make it go to the left because why not? All right, so that is the velocity of the river relative to the shore. And you notice I made it a little bit shorter because it's less in magnitude than this one. Now the vector sum of these two is going to be the velocity of the boat relative to the shore. Unlike the conceptual examples we talked about, these are not in the same direction or opposite directions. They're at a right angle to each other. But we still add them as vectors. So that means that our VBS is going to be the vector sum of these two, which is going to look like this, the connector. We've done this before when we were just doing straight up vector addition. So we've got V of the boat relative to the shore. And you can see that because the current's pushing it to the left, it doesn't move straight across the river. It moves this way. And that's why they can ask questions like, how far downstream will it be? Because it will not be straight across the river. Okay, so first things first, let's actually find the velocity of the boat relative to the shore. And we said that that's the vector sum. Well, these guys are at right angles to each other. So that means that the velocity of the boat relative to the shore, using the Pythagorean theorem, is going to be the velocity of the boat relative to the river squared plus the velocity of the river relative to the shore squared. This squared plus this squared, take the square root, and you wind up with 2.21 meters per second. Okay, so that's how fast it's going. But since we're talking about velocity, we need to know the direction as well. And so there's an angle here that we are trying to find. And what you might be able to see here is that if you look at this angle, that's the opposite side, that's the adjacent side. So the tangent of that angle will be the ratio of VRS over VBR. The angle itself will be the inverse tangent of those two quantities, and that's 1.20 meters per second over 1.85. And I don't need to write the units because they cancel, and I get 33 degrees. Okay, so now I know the actual heading of the boat, 2.21 meters per second at 33-degree angle that we've drawn in here. All right, now for part B, if the river's 110 meters wide, how long will it take to cross? That means that this dimension from here to here is this big. And if I think of speed equals distance over time, that means that, I'm going to just write V equals distance over time. That means that the time it's going to take is going to be the distance over the speed. Question is, which speed do we use? I got 3 speeds here. The quick and simple answer is, use the speed that's in the direction that you're talking about. The river is measured straight across, so we want the speed that we're traveling straight across. Even though the boat is actually moving 2.21 meters per second relative to the Earth's surface, the rate at which it crosses the river is the vector component that points in that direction. So I can take that 110 meters and divide it by 1.85 meters per second. And I wind up with a time of 60 seconds. And the other question is, how far downstream will it be? Well, again, if velocity equals distance over time, distance then, world's worst looking D, is velocity times time. Now the question again is, which velocity do I use? Well, I want to find how far it went downstream, so take the velocity that points downstream, which is the velocity of the river, and that's going to be 1.20 meters per second times the time of 60 seconds, which is going to put us 72 meters downstream. Voila.